All right. Hi, everyone. Welcome back. What we're going to do now is just go over a couple questions that JP has curated from the first batch of content. We'll spend a little bit of time going over that now and then dive into the second section.
Sounds great. Thanks, Kyle. We have plenty of questions. There's no shortage of them. So we'll try to get to as many as we can in the short time that we have right now. But one question that I had, you mentioned a product very quickly, sort of in passing, and it's a product that I use and I know is very valuable. And I wondered if you could quickly just kind of comment on Census Reporter.
Yeah, absolutely. Something that I think reasonably I could do right now is just visit there. And it's at censusreporter.org. And if you're not using Census Reporter, it is a phenomenal resource. So basically what you can do is you can browse through and you can grab basic facts. You can even do some data visualizations. There's data available for you. But what's very, very useful for me is to use their interface to go through and really have an alternative to load variables for trying to figure out what you're looking for. If I'm looking for, say, education, I can type this in and I get back all of these different possible examples for ACS tables that I might want to use to look at educational attainment. And so, for example, I could go to the basic documentation for education, and you can even see what you get back here. It shows you the questions that people actually answered on the American Community Survey. And so oftentimes this is really, really useful because at the end of the day, when you're working with aggregate data from the ACS, it's data that's been aggregated up from all of these different questions that people have filled in. And then I can go down and I can look at all of these different tables that I might be interested in. Here I have table 15003, which is the one that I most commonly use. I can click there and I see all of the different columns in the table. I see what the universe is. I get some more topic pages that tell me about the questions that were asked. And it really makes a lot of this information a lot more accessible. So I tend to recommend a fairly multifaceted approach to working with and figuring out what you want to look at with respect to census data. You can go in, I've tried to create tools that are usable and helpful for finding data, but it's not the only resource that you should be using. And so Census Reporter is pretty fantastic, I think, for the reasons that I've shown and a lot more.
Absolutely. I like it for the same reasons. So we have another question about the API key that's in RStudio Cloud. So we have a question asking, can I use the API key that exists in RStudio Cloud Workspace in my own RStudio running on my desktop computer?
You can use it for today. I wouldn't recommend using it longer term. I would get your own. Now, it's not like this API key is tied to, say, an account that anyone is paying for. And it doesn't usually happen, but it can happen if you're using, say, an API key that's kind of publicly out there, and then someone starts really going crazy and overusing the API, that key can get blocked. And so then you don't necessarily have control over the key that you're using. So get your own key, store it using install equals true if you're on your own computer, and that's what I would recommend. So I would recommend everyone in attendance get your own API key. You can use this key for today just so that we can get up and running, but I would get your own.
Now we have a few questions about the RStudio environment, RStudio Cloud environment. Asking how long will the cloud environment be available? There are a few people who want to use it either for themselves in the days ahead, or others who want to be able to show either their colleagues or their students RStudio.
Absolutely. So this is what I would recommend. Our studio gives you 15 hours, or I believe it's 15 hours of usage time for free per month. So if you want to use our Studio Cloud for free, 15 hours, and you're using it as an actual sort of cloud computing environment, that gets eaten up pretty quickly. For something like this today, it's great because we're just here for a couple hours and we can go and we can run it. But there are a couple of things to be aware of with our Studio Cloud. You'll notice that it says up here that it's a temporary copy, which means it's ephemeral. It's going to go away if you don't save it to your account. If you click Save a Permanent Copy, what it'll do is it'll bring that into your actual account and make a project for you that's copied over from my original project that I made. Now it's yours, and it's going to live in your account as long as you have that account. There are some limitations. There are limitations on the number of projects you can have and the number of hours, that active hours per month, and so with the free solution. So if you're looking for a more robust cloud computing solution, uh, our Studio Cloud does have paid plans. For example, another issue is you only get 1 GB of RAM with the free account, which for serious data analytic work is not going to be enough, most likely. So we, even with this script, we kind of push it all the way up to the max just with this script. So this is a great way to get started. It's not going to go away if you save it to your own account. So that's great. But make sure that you do that. And if you need more horsepower, so to speak, consider getting one of the paid plans. If you are an educator, they do, I believe, work with teachers quite a lot and give discounts. So I would strongly recommend taking a look at that.
Here's I think, a fairly quick question. Does the 1 year default to the most recent, the 1 year, I think, get ACS default to the most recent year?
It always does, not when I update it. So basically what I try to do is I try to keep the package as updated as possible. And what that means is that I will go in every time that there's a new data set released, specifically a new 5-year data set released, and then I will release a new version of the package that defaults to that data set. So at the moment, the default data set is 2019. That's the most recent data that we have. That will remain the default all the way up until December of this year, when the 2016 to 2020 ACS is released.
And if a user wants a different vintage, is that possible?
Yes, you can use the year argument. So I'm going to jump back here to RStudio, and I didn't highlight this, but I did use it here in this Wisconsin income code. So this grabbed data for the 2015 to 2019 ACS. Let's say I wanted 2012 to 2016. I just say year equals 2016. I run that. It tells me I'm getting data from the 2012 to 2016 ACS. And we have support going all the way back to, at least for the 5-year ACS, 2005 to 2009. So not every variable is available in the 2005 to 2009 ACS, but a lot of them are. And so there's a pretty good time series available.
Okay, great. One final question. We have several users who are very interested in small level geographies, blocks,
Okay.
block
Yeah,
groups, and census
absolutely.
tracts. Most of them are asking, is it possible to grab all census tracts or all block groups, or at least for one user, all blocks for the entire nation?
So yes, with an asterisk. You absolutely can, but Tidycensus is not designed for that because the Census API is not designed for that. So there are 11 million or so blocks in the 2010 census. The 2020 geographies just came out. We'll talk more about those next week. I don't know how many blocks there are in the 2020 geographies, but that's a lot. So that's a lot of data for the API to return, and so invariably it gets limited. You can't just go into the API and say, give me all 220 or 230,000 block groups for the US in a single API call. Instead, block groups, they used to only be available by county. Now they're available for some of the vintages by state, but that's a little uneven at the moment. And so assembling these data sets for the entire country, what Matt and I have done is try to put together some internal functionality that combines data. So it'll hit the API multiple times and combines data as best as it can, but it doesn't do this for the whole US. So you can get county level for the whole US, but for census tracts and block groups, you're going to need to go by state. That said, what you can do, and this is a little bit slightly more advanced programmatically, you can use an iterator. So if you're familiar with the per package, the map functions in the tidyverse, that's what I tend to use. You could iterate over a sequence of states or state names and use a function, say like mapdf, to stitch them all together. You'll just end up hitting the API a bunch of different times and then putting it together. I do get this question some. Well, I want all 11 million blocks in the US. Couple different options for you that I would probably take a look at. If you want to use R, there's a package called Tidycensus that is a little different from Tidycensus in that it doesn't hit the API. And what it does is it downloads from the FTP server full census data sets and stores them on your computer, and then gives you functions to sort of query and load in those data sets. You might want to look at total census if you want an R-based solution for grabbing all the data for the United States. Tidycensus isn't really made for that. The other option that I strongly recommend, because I went to the University of Minnesota, but not just because, is the National Historical Geographic Information System, or NHGIS. NHGIS, if you're not familiar, is a phenomenal project that has a team of researchers who have done the hard work of harmonizing census data over time. They have aggregate data and geographies going all the way back to 1790, which is amazing. And you can get bulk downloads of data from there. They do have an R package, and they do have a data download API. The IPAMS R package allows you to access NHGIS data. So that might be a solution for you. You can do it in Tidycensus, but you are hoping that if you're hitting the API a couple hundred times, that you don't have an internet hiccup. So some of those other solutions might be preferable.
Great. Thank you for those. We'll hand things back off to you for the second hour.
Okay, sounds good. I'm gonna need to mute and video off for 2 seconds, get resituated, and we'll get things started. All right, so let's delve now into hour 2. So thanks, JP, for those questions. And we're going to jump back over to the slides here. So part 2, we're focusing on wrangling census data with tidyverse tools. And I've mentioned before that I designed Tidycensus because I wanted the data that I use on a daily basis in my work in a format that is ready to go for analysis with the tools that I use on a daily basis in my work, which is tools in the tidyverse. And so a little bit of background about the tidyverse. The tidyverse is an integrated set of packages. Originally, way back, it was called the Hadleyverse after Hadley Wickham's work in this area, the chief scientist at our studio, but it was renamed the Tidyverse because it has a lot more contributors now than just Hadley. And it's housed over at our studio. And the goal of the Tidyverse is to create an integrated sort of set of packages that are designed to work together and allow you to kind of streamline your data analytic workflows using very straightforward syntax. And so the Tidyverse, for those of you who are R users and knowledgeable R users, that's going to be familiar to you. And if you're not familiar to R, the Tidyverse is a nice way to get acquainted with R. It's an opinionated way of doing data analysis. It aligns very well with how I do work. There are a lot of different paradigms that you can use within R, but the Tidyverse is my personal favorite. And so I've tried to develop Tidycensus to align with the Tidyverse as appropriate. And so within the Tidyverse, we mentioned this before, thinking about design philosophy. Going back to that last topic that we talked about, census data are commonly used in wide format. And we talked about the distinctions between long and wide form data. Wide form data has those variables spread across the columns. And we saw some examples of that in the previous section of this workshop. If you're working in a GIS context, in a spreadsheet context, maybe in, say, an SPSS context, wide form data is probably what you're familiar with. And there are a lot of applications where that makes a lot of sense. Tidyverse tools, however, work better with long form data or tidy data. And I'll show you why in just a moment. There are a variety of methods that we can use within the Tidyverse that the default long form or tidy format of census data that's returned by Tidycensus allows you to just plug that data right into a Tidyverse analytic workflow and start generating insights right away. So the first set of examples that we're going to look at involve data exploration. This is a really important part of data analysis. You know, sometimes the more fancy analytic techniques or programming techniques or statistical models get the attention, but there's tremendous value to just being able to go in and say, what are the largest values of this in the US, or what is the youngest county in the US? Just being able to know how to do that is extraordinarily valuable. And we can do this in a fairly straightforward way with Tidyverse tools. So we're going to take a look at a variety of Tidyverse functions, generally speaking, coming from the dplyr package. So the dplyr package is really one of the workhorse packages within the Tidyverse. It has got to be, I would think, one of the top 5 or top 10 most downloaded packages in all of R. And its functions are heavily used, especially if you're coming from a database background. They're heavily used to do data manipulation, similar to what you might commonly do in a SQL database. I need to create a new column. I need to sort my data. I need to query it. dplyr has functionality with sort of clear verbs to facilitate that. So we'll take a look first at answering some questions using Tidyverse tools. We're going to look at the arrange function, which sorts data based on one or more values or one or more columns, and the filter function, which allows you to query your data based on an expression. So let's try to answer this question. And maybe some of you who are seasoned demographers know the answer to this off the top of your head, but I'll be honest, I don't have this memorized. You know, what are the youngest and oldest counties in the United States by median age? And there are vast disparities in the United States along these lines. So let's grab a little bit of data and take a look at this. So I'm going to jump back over to R here, and I'm going to scroll down to this median age section. So let's grab this data, load in the Tidyverse package, pull in the data, you'll notice at the county level, we can very quickly grab data for all counties in the US. And let's take a quick peek at our data. So this data set has not been sorted in any capacity. It's just coming in as it comes in by default from the API, which is in order of GeoID, and which effectively is alphabetical order by county and state. And so we see here median age. You've got counties in Alabama, which tend to have median ages, late 30s, early 40s. But there are wide variations in this particular variable and those values across the US. And so let's get started exploring this a little bit. The first thing that we're going to do is sort our data in ascending order. That'll allow us to see what are the youngest counties by median age in the entire United States. So we use the arrange function here. The first argument is going to be our data set, and the second argument is going to be the column name that we're going to look at. We don't have too much time to get into how the tidyverse handles something called non-standard evaluation, which basically allows you to put variable names in as that are unquoted to save you some keystrokes. But if you're interested in the design philosophy of the tidyverse in that capacity, I would strongly recommend reading up on it. So if I run this code here, arrange my median age data set in order of estimate, let's run it. I get back my same data, but ordered in ascending order of median age. So I can see now the youngest counties by median age in the US. You'll notice that the two youngest quote unquote counties are not in fact counties at all. So the counties from the API and the census include counties and county equivalents. And if there are any of you from Virginia, you'll be very familiar with this. If you're not from Virginia, you might be a little less familiar, but Virginia has both counties and independent cities. And so Lexington, which I believe is where the Virginia Military Institute is located, is it has the lowest median age of any county or county equivalent in the United States at 22.3. You'll notice a few other counties that come in: Todd County, South Dakota; Madison County, Idaho, which is around Rexburg, Idaho; Whitman County, Washington; Clay County, South Dakota. And so you can browse through this if you want to. You can view your data as well. So another way that you can interactively do it, and I should show you this, is I could pull up my median age data set in the data viewer, and I can actually interactively sort my data just like you would in a spreadsheet. So that's a handy feature as well, if you want to do it interactively. So we've seen the youngest counties or county equivalents. What about the oldest? If we use this desc function in the tidyverse, I can say, give me back counties in the US arranged in descending order of their median age. So let's run that through and let's take a look at the oldest counties in the US. Sumter County, Florida is by far the oldest county in the entire United States, about 6.5 years older in terms of median age than the second oldest county in the US. And for those of you who know Florida, it's of course a very popular retirement destination, but Sumter County is home to a community called the Villages, which is one of the fastest growing communities in the entire country. And much of it is a planned community for seniors. And it's sort of a fascinating demographic example in this capacity, but it gives Sumter County a median age of over 67 from the most recent ACS estimates. You can see a few other counties, largely rural counties across the US, couple in Virginia, got one in Michigan. Those Michigan counties are up in the Upper Peninsula. So we have some older populations up there. But you can see how with these tidyverse functions, you can, in a relatively straightforward way, start to explore your data a little bit. The second piece that you might be interested in is taking a look at grabbing subsets of information based on values that might be in, in various columns. And so we've looked at arranging our data, but what if we want to know, well, what are the oldest counties in the US, or how many counties in the US have a median age greater than or equal to 50? The filter function allows us to subset or query our data based on an expression. And so in this particular example, I'm creating a new object called above 50. That is the result of filtering my median age data set only for rows where the estimate column is greater than or equal to 50. If I jump back to R and I run that code through, I see that I get a data set of 216 counties. So there are 216 counties in the United States that have a median age of 50 or greater. If I want to, I can open up my interactive viewer and I can browse through that a little bit. And you can then go through and find your state. So I'm located here in Texas. I might scroll down a little bit and find all of those counties in Texas that have a median age above 50. So we've learned a little bit about how to take a look at our data, explored a little bit with respect to sorting it in descending and ascending order. I even tell my students this. It's such a common operation that we do in spreadsheets that we don't always think about how powerful that is. Being able to know what is the biggest, what is the smallest. I tell my students this when they're learning Python. I teach Python at TCU. Sorting your data is a data analytic technique. That's something where you're generating new information that, might not be common knowledge to people. And so we can do that relatively seamlessly within the tidyverse. Something to think about, however, in terms of how many variables in the ACS and the census are organized. They're organized into tables in which, in some cases, and in many cases, honestly, the very first variable in the data set or in the table represents a summary variable. It's the appropriate denominator for which all of the other variables can reasonably serve as a numerator. For example, in the age by sex table that we looked at before, the very first variable is total population. And so that's the corresponding denominator. A good example of this is education, because educational attainment is reported in the ACS for individuals age 25 and up. It doesn't really make sense to ask a 16-year-old if she has a PhD. You wouldn't expect that that would be the case at that particular stage in your life course. And so the appropriate denominator when measuring educational attainment is not total population, but rather is the universe of people age 25 and up. And so census will organize the tables accordingly. There's functionality in Tidycensus to sort of create almost a combined or fused long and wide table that allows you to have your data in long form, but then tacks on a summary variable and a summary estimate in the case of the ACS that can be used to normalize your data. Because, as analysts, this is something that we have to deal with all the time. We're less interested in knowing, say, which county in the United States has the largest Hispanic or Latino population. Those are going to be just the largest counties by population in the US. So Los Angeles County is going to come through no matter what. We might be more interested in normalizing that by the total population and say which counties have the greatest proportion of their population that's Hispanic or Latino. That's often of more interest to analysts and demographers. We can normalize our data using tidyverse tools and summary variable functionality. So let's take a look at how to do that. What I'm defining here is a named vector of variables for 6 different racial or ethnic groups. I'm pulling from the table B03002, which is Hispanic or Latino or not Hispanic or Latino by race. So for white, this will represent non-Hispanic white. For black, this will represent non-Hispanic black, so on and so forth. We're going to grab that information for counties in Arizona, but notably, we're going to specify a summary variable. with the summary var parameter. The summary variable is the total population for whom race and ethnicity is determined. And so that allows us to look at percentages or proportions. So let's pull that data in and take a look at it. I'm going to pull down all that data. And this is what I get back. We have here a data set that has 7 columns instead of 5. We have our GeoID, so our county ID code. We have our county name. We have the variable replaced with the names that we gave the variables. We have an estimate and a margin of error. If you see an NA in the margin of error column, it means oftentimes that margin of error is controlled or not reported for a variety of reasons. And then we have a summary estimate and a summary margin of error if appropriate. In this particular case, total population, that estimate is controlled, and so it's not reported back with a margin of error in that particular context for these counties. And so what we can do now is take a look at the estimate and then compare that with the summary estimate, which is total population. So for each category, what we can do is in turn normalize our data and calculate a proportion or percentage. We can do that with functionality in the tidyverse. And so jumping back to the slides here, we're going to take a look at a couple other functions in dplyr that are going to be a common portion of your workflow. And you're going to learn about a new operator, the pipe operator from the magrittr package, which is commonly used in the tidyverse. The mutate function in dplyr allows you to calculate new columns in your data. And so this is a very common thing that you need to do in data analysis. Take a value in one column and another column and divide one by the other, add them together, or apply some formula to it. Mutate allows you to do that. The select column then allows you to retain or drop columns by name. So whereas the filter function basically subsets your data set by values in the rows that correspond to the rows, the select function allows you to either keep columns or drop them if you don't need some of the columns. And so the pipe operator, for those of you who are less familiar with R or the tidyverse, allows you to create a chain of methods, so to speak, or a pipeline of methods in which the result of one operation is carried through to the next operation. This is a great way to organize your code and not have to grab line after line after line, but rather link everything together and show how an integrated data analysis works. So in this particular case, we're creating a new object named AZ race percent. And it's calculated based on where we take the AZ race, the Arizona race data set, and you can pronounce the pipe as then. So you can read this as, take my Arizona race data set, then use the mutate function to create a new column called percent that is the result of this operation, 100 times the estimate divided by the summary estimate. Then select 3 columns that I want, name, variable, and percent. That's how potentially you can read that. And so in this particular example then, let's run it and take a look. I now have back a data set in which I have the county name, I have the variable corresponding to each kind of, again, county variable combination, and I have the percentage. So Apache County is about 18.2% non-Hispanic white, about 0.5% Black, 73% Native American, and about 6% Hispanic, and then small populations of Asian and Hawaiian and Pacific Islanders. And now I can make these comparisons both across counties and across different groups. The next data analytic workflow within the tidyverse that I might argue is the most powerful functionality available in the tidyverse is group-wise census data analysis. And I'll tell my students this all the time. Being able to implement group-wise data analysis allows you to generate all sorts of insights that are going to be conceptually straightforward, but not always computationally the easiest thing to do if you're not working within a paradigm, say like the tidyverse or one of the other data analytic frameworks that people use in an R or a Python. And being able to say, okay, for every salient group in my data set, give me back information about it. That's something that in census data workflows is very commonly used. And I think Tidycensus sets up pretty well with the tidyverse to allow us to do this. Your workhorse functions here to implement the split apply combine method of data or method or model of data analysis are going to be group by and summarize. The split apply combine model of data analysis or method of data analysis, it's going to be familiar to some of you, but for some it might be less familiar, but it's conceptually fairly straightforward. You take a data set and you identify some sort of characteristic of your data in which you can split the data set. For example, I might say, okay, I have a bunch of information for Apache County, I have a bunch of information for Maricopa County. Let's split my data set by county. I then apply a function to each of those counties. You might say, okay, we're going to look at this. What is the largest group by county? And then once I have that information, I combine it back into a final data set that allows me to cleanly make comparisons across counties. So let's take a look at how this works. Let's ask this question. What is the largest group by county? A group by and a filter can be used to do this in a fairly straightforward way. We read this code as, give me back a new data set called largest group that's derived from my Arizona race percent data set. Take my Arizona race percent data set, then group it by the name column, which is going to be our county, then filter that data set where the percent column is equal to the maximum value in the percent column for that county. Stitch that data back together, and let's see what we get back. So going back to R here, let's try running this. I get back that result very, very quickly. And so for the 15 counties in Arizona, I can now see what the largest group is by county and what the percentage is. And so this is an interesting way of kind of analyzing and looking at our data. So Apache County, the largest group, we saw this before, is Native American with a percentage of 73%. Maricopa County, the largest county in Arizona by population, non-Hispanic white is the largest group with a population of 55%. So a smaller proportion. And you can see this here. Santa Cruz County, for example, the largest group is Hispanic. Over 80% of its population is Hispanic. Yavapai County as well, largest group is white, over 80%. These counties are less diverse. Some other counties like Navajo County or Greenlee County, the largest group constitutes a plurality, but not a majority of the population. And so these counties, we get the hint that they're a little bit more diverse. And so we've used these tidyverse methods on our census data to be able to, start to answer some of these questions and make comparisons across groups. We might also be interested in a workflow where we ask, well, okay, I'm trying to get a little bit of a sense of how racial and ethnic diversity varies across these different counties in Arizona. Maybe I take a look at what the median percentage is for counties in Arizona by group. And here I'm using a group by summarize workflow. I take my Arizona race percent data set, then I group it by the variable column in this case, which is going to be the racial or ethnic category. And then I summarize by taking and create a new column where the median percentage is calculated with the median function here. Let's try it out. I can run that through. And I get back some information. The median Asian percentage in counties in Arizona is just under 1%. The median non-Hispanic Black population percentage for counties in Arizona, just over 1%. The median white population, 54%, median Hispanic, 30%, median Native American population, only about 3.5%, even though some of the counties have very large Native American populations. And you could fiddle around with this and try different functions too. You could look at what's the maximum, what's the minimum, what's the mean, if you want the mean instead of the median. All of that is possible here. Now, moving into kind of the last component of this hour of our work on sort of data wrangling in the tidyverse is working with margins of error in Tidycensus. We haven't talked a lot about margins of error yet, but they're really critical to acknowledge and pay attention to when we're thinking about working with American Community Survey data. So we've looked at this already, and we've mostly been looking at ACS data in our examples to this point. If you're working with decennial census information, you won't have that margin of error. But if you're working with ACS data, which you commonly will be because it's more up to date and it has more variables that you can draw from, you're going to need to acknowledge and deal with the margin of error. And as mentioned before, the ACS is a survey. It is not a complete enumeration of the US population. It's a survey from which characteristics of the population are inferred. And in turn, like any survey, those estimates are going to be subject to a margin of error. I mentioned this at the beginning of our workshop today. By default, margins of error are returned at a 90% confidence level. And so roughly you can say we're 90% sure that the true value, whatever it is, falls within a range defined by the estimate plus or minus the margin of error. Within Tidycensus, now I've sometimes had some requests from users who say, I don't want the margin of error. Why do I have to get it back every time? And this is a design decision that I made at the outset. If you're using ACS data, you need to at least know what that margin of error is. As an analyst, at the end of the day, we're all responsible for the analytic decisions that we make. But these are not true counts. That's not what they are. They are estimates from a survey that are characterized by a margin of error around that estimate. And so Tidycensus always gives back the margin of error. Wide form, long form, doesn't matter. And so margins of error by default, as we've seen in long form or tidy data, are in the MOE column, or in wide form data, an M suffix is appended to the margins of error. There is an argument that you can use in GateACS, MOE_level, MOE_level, that controls the confidence level of the MOE. So if you want it to be a little bit stricter, you can change it from 90 to 95 or 99. So let's take a look at why this matters. I'm going to grab here some data on population over age 65 by sex for census tracts in the Salt Lake City area, so Salt Lake County, Utah. We're grabbing from the 5-year ACS, the most recent 5-year ACS. And you'll notice I'm doing a little bit more advanced code here where I'm using the paste zero function to construct a vector of variables that I'm passing to the variables argument here. Let's take a quick look at this. Population over age 65 by sex, by census tract in Salt Lake City. What do the margins of error look like? I've just grabbed a sample census tract to take a look at here. We run this through, and let's take a peek at it. Look at what we get back. And this is default information at the tract level. And the tract level is not even the smallest geography we get in the ACS. We can go down to the block group, which is smaller. For many estimates that you will see, especially as you start to get granular, the margin of error exceeds the estimate. So basically, you're looking at information like here, and this is basically men age 65 and 66. The estimate is 12 in the census tract plus or minus 13. And even conceptually, you have to think about this a little bit. It's very possible that there aren't any men in that age bracket that live in that census tract. There might not be any there, but there might be, all the way up to 25. And we're only 90% sure that it's within that range. So uncertainty is very much baked in here. And that's important as analysts for all of us to be thinking about when we're working with this information. And you might start thinking, well, I've been using ACS data for a while. I mean, I knew the margin of error was a thing. Does this mean that I can't use this information? Does this mean that, these estimates are invalid? That's not what it means. It means that we all need to understand that these are estimates characterized by uncertainty. And the Census Bureau does not recommend that we treat these estimates as counts. When you see the number 36, it's not meant to say there are 36 people here. I'm a service provider. We need to prepare 36 packets to deliver there. That's not what it means. It's meant as an estimate that allows for comparison between places. So we think there are more people here in this particular age bracket because there are 36 than there are in this particular age bracket, which is B01001-044. It allows us to make those comparisons. And those comparisons are still really valuable, but it's important to interpret your data in a different way than you would in the decennial census, in which the values are meant to be counts of the population. One potential resolution, however, to this issue in the ACS is to use tidyverse tools and tools that we've written into Tidycensus to aggregate up your data and calculate new margins of error. And so I want to show you some examples of that. In Tidycensus, there are 4 margin of error functions that implement census recommended formulas for calculating derived margins of error. So you might say, if I'm adding estimates together, or if I'm dividing one estimate by another, what's the margin of error for that derived proportion or that derived sum? Well, we have functions that help you out with that. MOE sum calculates a margin of error for a derived sum, MOE product for a derived product, and then MOE ratio and MOE prop for proportion, depending on what your division looks like, calculates margins of error for a ratio or proportion respectively. And so the MOE prop function, just a basic illustration of how it works, we can run that through here in R. So if we look at the arguments for MOE prop, and if you're ever interested, if you're new to R, by the way, I probably should have mentioned this before, you can grab the help documentation for any function by typing in a question mark and then the name of the function that you want documentation for. So here I type in question mark MOE underscore prop, and now I get help documentation for it. So that MOE prop function takes as the first argument your numerator, the second argument your denominator, the third, the margin of error around the numerator, and the fourth, the margin of error around the denominator. So in this particular case, let's say I have an estimate of 25 with a margin of error of 5 around that estimate, and then a summary estimate, so my denominator where the estimate is 100 with a margin of error of 3. So what's the derived margin of error? And my margin of error then is going to be about 0.05 around that derived proportion. So Tidycensus can help you out with that. Finally, as we look at this here, the group by and summarize methodology in dplyr and in the tidyverse can sometimes help you out when dealing with some of these relatively large margins of error. In this particular case, what I'm doing is I'm taking all of the information about people over age 65. I am parsing out and using a little bit more advanced code here to identify the sex. So here I'm parsing out male and female. I'm grouping by the census tract and the sex, and I'm creating new estimates and margin of error columns for people over age 65 by census tract by sex in Salt Lake County, Utah. What I get back when I run that through, let's take a look at it, is a data set that has collapsed my data. It's collapsed my information. Here is this census tract here in Salt Lake County, Utah for women over age 65. Here's the summary estimate. And we notice now, relative to the estimate, the margins very much reduced. I would encourage you to read some of the articles in the Tidycensus documentation about margins of error for some other methods that have been recommended for handling and working with margins of error. But this hopefully gets you off to a little bit of a start. And I would encourage everybody, if you're working with ACS data, to give some thought to margin of error, what it means, and how it influences really how the estimates are meaningful that you're working with and analyzing. All right. That takes us to the end of part 2. So let's take another 10 or so minute break to ask some questions, work on some exercises, stretch your legs a little bit. Here are some exercises that you could play around with in the interim while we're taking a little break. So we've been working with the detailed tables in the ACS so far, but there are a variety of other aggregations that are available in the ACS that are pre-aggregated. So we can get subject tables and we can get the data profile by specifying appropriate variables. And so the variable in the 2015 to 2019 ACS data profile that gives you pre-computed percent of the population age 25 and up with a bachelor's degree is DP02_0068P. So try using this to determine, for a state of your choosing, the county with the highest educational attainment, the county with the lowest educational attainment, and then the median value for counties in your state using some of the tools that you've learned. So let's break for 10 minutes. We'll come back just after 3 o'clock Central Time, 4 o'clock Eastern Time, and we'll learn how to visualize some of this information.